So, can we still hear you? Yes. We're live on YouTube, and let's not waste much time anymore. Hello, everybody. Sorry for the being late with this talk. We had some trouble connecting. We are happy to have today Professor Shiming Wan from the Institute of Oceanology, the Chinese Academy of Sciences. He's has long-time interest in the Monsoon. He's a sedimentologist, has been working, and the veteran of the IODP. Now 3 expeditions at his portfolio. He's working with marine sedimentology to reconstruct the Monsoon in all shapes and forms. He's a long-time collaborator of Peter Clift and Christian Franz Lanord. And he's going to talk today to us about the evolution of the East Asian monsoon from tectonic to glacial timescales. And this from the perspectives of weathering records on the Asian margin. Welcome, Shiming. If you can share your screen.
Okay, thank you. Thank you, Liviu. I can. Okay, I just set the...
How it works, I'm so happy.
Yeah. So Liviu, can I begin?
Yes, please.
Okay, sorry about the wasted time. Good morning or good evening or good afternoon, everyone. I'm Shiming from the Institute of Oceanology, Chinese Academy of Sciences. Firstly of all, I want to show my thanks to Professor Peter Cliff, Liviu, and Tara for their kind invitation and this nice organization of the Monsoon Seminar. And today, I want to talk about the evolution of the Asian monsoon from tectonic to glacial timescale perspectives from weather records in the Asian margin. And this is a study for the past several years, and many people contributed to this work, including my students and my colleagues, and also Peter. And here, I'm not just going to only talk about the monsoon itself, but more about the links between weathering and the monsoon. And as we know, their links is often not so simple. It's very complex. It's not just one-to-one. And we try to use the traditional records in the marginal seas to trace the past changes of weathering onshore and their links to monsoon and other climatic and tectonic evolution on the geological timescale. First, we know that silicate weathering plays a significant role in the Earth system because it not only shaped Earth's landscape and also control the delivery of sediments and solutes to the ocean. And also it supplies some key nutrient elements such as the nitrogen, potassium, and the iron for the plants, for the life on the Earth. More important, as the important sink of carbon, and the silicate weathering can regulate CO2 level just by buffering excess CO2 disgust from the Earth's interior to the surface, and so keep the surface temperature of Earth in a relatively stable range. So it can affect global climate over geological timescale. So silicate weathering can influence monsoon climate, but also more dominated or influenced by climate. And because basically the silicate weathering is a chemical reaction between water and rocks with the help of dissolved CO2 in the groundwater, such as canic acid. And so it's clear that the temperature, the precipitation, and the CO2 level can influence the process of chemical weathering. Moreover, that the monsoon rainfall can also dominate the soil erosion and the sediment transport. That's the weathering products transport from the source to sink, from the mountain to the ocean margins. So the whole process from chemical weathering, soil erosion, and the sediment transport can be influenced by the monsoon climate. However, just as I said, the links between weathering and climate is very complex, and the interaction and the weathering is, in fact, is the interaction between lithosphere and many other layers of the Earth, including the atmosphere, hydrosphere, and the biosphere. And there are many factors, including CO2 level, temperature, precipitation, vegetation cover, rock type, relief, and tectonic activity can influence the process of chemical weathering. And these factors can, most cases, they can be related with each other and ascribed to the climatic factors. In contrast, the tectonic factor in some cases is very important. For example, in the conditions of weather limited condition, such as Taiwan, and with the very steep relief and very strong tectonic activity and very strong the rainfall and the typhoon, the seismic. So there will be very high physical erosion rate, and the sediments can be not the fully chemical weathered before their erosion and transport to the deep sea. So we'll see the sediment have very low chemical weathering intensity, even there is a high rainfall. So seems that there paradox between the weathering and climate. So sometimes we should be very careful about their interpretation of their links. Sorry, but there is it cannot work. Oh, okay. As to the Asian monsoon, we know the monsoon is basically defined as the seasonal reversal of wind direction and of wet-dry climate because of the difference, because of the thermal contrast between the ocean and the continents. And when the summer monsoon is coming, usually we will see the raining and hot occur during the same period. For example, just like in Guangzhou and Helei city, we'll see the temperature and the rainfall that correlate with each other and occur during the same months and during the summer. So in this case, we can just simply regard the monsoon as a circulation of water and heat, especially in the low latitude regions. And its evolution plays a significant role in our understanding the regional and global climate, because it is a significant component of the global monsoon and global climate system. And because as the most important climate system of Asia, the Asian monsoon dominates the seasonal precipitation, runoff, and chemical weathering, soil erosion, and sediment transport from land to the sea. And we see this close relationship between the water discharge and the sediment yield of the major Asian rivers. So this indicating the strong monsoon control on the soil erosion and sediment transport. And just because of the high mountains and the abundant rainfall in Asia, there are many world-class rivers in Asia, such as Yellow River, Yangtze River, Pearl, Red River, Mekong River, Irrawaddy, and Ganges and Brahmaputra. So all these rivers contribute a total of 7,000 million tons sediments and dissolved loads to the Asian margin seas, that accounting for around 30% of global budget. So the Asian part in terms of sediment transport is very important on the global scale. After the sediment was transported and deposited in the margins, and the formed strata will become ideal materials or caves to reconstruct the weathering onshore. And so we just use the proxy records weathering proxies from the sediment core drilled in the Asian margins to reconstruct the weathering on the continent and their links to the monsoon climate or any other climate parameters. Usually the proxies we use the Claminus ratios such as the kernite to inlet ratio or smectite to chloride ratio, and also the CIA potassium to anion. And both these ratios mirror the loss of immobile elements during the process of chemical weathering. And kernite is usually formed under the warm and humid climate, tropical regions, and with the very good drainage condition. In contrast, the inlet is a product of physical erosion of bedrock, or just the chemical weathering or some feldspar and micro and the moderate hydrolysis. So also terrestrial flux and hematite goethite. And many pressure studies have shown the close relation of chemical weathering proxies and climatic parameters. For example, the chemical index alteration, the CIA of the suspended sediments in the Asian region, Asian major river basins shows a very close relationship with the temperature, precipitation, and runoff, suggesting the monsoon control on this weathering. And so this is modern observation. For the past change of proxy records, and there are also some studies shows the high resolution of clay minerals just offshore the Mekong River and in the South China Sea to show the clear response to monsoon evolution of the weathering proxy. So here I want to show two examples from the tectonic to orbital timescale, and we know that on different timescales, from the tectonic, the million years to 10,000 years to 1,000 years or 100 years, the evolution of Asian monsoon have very different forcing mechanism. Under the first one is tectonic timescale monsoon evolution. This is long-term evolution of Asian monsoon. And if we look at the global distribution of deserts, it will be very, very interesting to note that most of deserts that locate in the subtropical latitude, and like this. So this, in contrast, is very different for the Asian part, which is characterized by the humid climate in the South Asian and the East Asian, but a very dry climate in the Central Asia. So this is because of the existence of Tibetan Plateau. And so this also is just the typical, the modern monsoon pattern. So one important question is, when was the modern Asian monsoon pattern established? So the earlier studies that including the both South and East Asian records, such as the C4 plants expansion in Bajistan in the South Asia and upwelling proxies in the Arabian Sea, and also the onset of red clay in the North Plateau, and just like suggest a stronger Asian monsoon at 80 million years, and link it to the uplift of Tibetan Plateau. And however, the later studies shows that the Asian climate that become drier but not humid after 80 million. So the monsoon history should be much older than 80 million years. And later, important studies that using the onset of Earth deposition in the Western Earth Plateau, and also the large-scale distribution of pollen, gypsum, and other fossil records across the whole China. That shows an important climate organization at around 22 million years. And so this was suggested as a transition from the zonal to monsoonal climate pattern in China as an Oligocene to Miocene boundary. So this is very important. However, there's also some new studies that show challenge this opinion, that suggests the existence of East Asian monsoon already there in South China in the Eocene. So there's okay, this is still in debate for the monsoon initiation time. In any case, so what drove the monsoon initiation or long-term evolution? There are at least three possible factors. The first one is Tibetan uplift, Tibetan Plateau, because the GCM modeling shows that the much larger and higher plateau or the need to drying Asian inland and stronger summer and winter monsoon by increasing the insensible heating and latent heating. Here, I want to emphasize this because this character is very important. Just the high mountain will drove both winter and summer monsoon. I will mention this later. And the second one driver is the retreat of Paritatic Sea. The Paritatic Sea that exists over the large areas of Central Asia that during the late Eocene to Oligocene. So it can largely influence the climate, regional climate in the Central Asia, and even the Earth plateau just at that time by providing important water vapor or moisture source to this area by the westerlies. So, however, the recent study shows that this Paritatic Sea mostly retreated from Central Asia during the early Oligocene around 32 minutes, suggesting that the long-term evolution of East Asian monsoon after that time should not directly relate to the retreat of Paritatic Sea. So this is reasonable. And the last possible monsoon driver is global climate change, such as global temperature, global ice volume, and CO2 level. So the famous study by the Glacial using snail and mammal fossil isotopes in the South Asia just suggests that seasonal monsoon already existed at 40 minutes ago at that's the Eocene because of the high CO2 concentration and temperature at that time. So this is very interesting. It seems like the monsoon is just a response to global climate change rather than topography uplift. So this is very interesting. So the key questions are how did East Asian monsoon develop and evolve through the Oligocene Miocene? And its monsoon evolution on tectonic timescale is in response to global climate or tectonic uplift. And here we just using a long sediment core from the U1501 in the northern South China Sea to constrain the source of clay minerals and its evolution, and also trace the long-term evolution of the Asian summer monsoon by the weather records. And this sediment core just extend to the 35 mini years. And here, the methods we're using, including the grain size distribution on the organic and carbon-free fractions. And the clay minerals, major and trace elements, and structure needle isotope focus on the clay syndicate fraction to exclude possible grain size effect on the proxy. And we know just before our interpretation of weather proxies is very important to constrain or to make clear the evolution of a sedimentary environment and the sediment source that's changed through time. That is very important because these processes can influence the proxy interpretation. And we use many proxies and to show that the environment, the sediment environment can be divided into 3 stages. The first one is between 35 to 30 mini years. The study area of the South China Sea is characterized by shallow water environment that is like at a upper slope or the shelf environment. And during this time, we can see that the very high terrigenous flux and coarser grain size and the high content of NGR and terrigenous materials and the low content of carbonate content and fossil abundance and the very high content of glaucite and low content of pyrite. So this suggesting that it's a high energy environment and also the sediment have not been transported over long distance before its deposition. So this is shallow water environment. And since the 27 million years, all the proxies keep relatively very stable trend, and since then, and also the content of carbonate is very high, suggesting a stable deep sea environment. And during 30 to 27 minutes, it seems the transition between the deep water and shallow water. So the long-term evolution of the sedimentary environment in the northern South China Sea seems to result from the strongly related to the tectonic evolution of South China Sea because of the early rifting or seafloor spreading in the South China Sea. And we further using the claminals and strontium medium isotopes to concentrate the sediment profile change since the 35 million years. And we compare the data of our study site with the potential sediment source, including Luzang rivers and Indochina and Taiwan and Southeast Glacial here block and the Pearl River, the South China and older Pearl rivers just before the late Holocene and also Balawan and Mindoro. And the result shows that the sediment for the start site that came from the between the 35 to 30 million years came from the Southeast Caucasia coast source. But during this period, the sediment is characterized by the smectite ridge and with the relatively positively Lidrum isotopes. And in contrast, since around 30 million years, the sediment came from Proto-Pearl River, the glacial interior. During that time, the sediment is elite and chloride rich, and with the relatively negative Lidrum isotope and a more higher ratio of strontium isotope that is close, similar to the Pearl River, modern Pearl River. And here we also using the many proxies shows how the prevalence changes through time. The Lidrum isotopes from U1501 and also previous studies from site U1148 and K feldspar percent for this site and smectite to elite ratio. And all these proxies just like shows that the very clear change from the prevalence from the southeast Caucasia to the Pearl River. The transition is occurred around 32 to 30 million years. So we suggest a modern neck Pearl River was fully established at 30 million years. That after large-scale westward expansion from previous, the small river drained through the Caucasia coast and moved to the Caucasia interior, just because of the uplift of the southeast Tibetan plateau and the subsidence of the South China Sea because of the seafloor spreading at that time. Oh, sorry. So after the provenance reconstruction, and then we can use it, we can see that the sediment source and sediment environment is stable since 27 million years. Now we can use the material since that time to reconstruct to long-term evolution of weathering in South China in the source region, and thus reconstruct linked to the East Asian summer monsoon evolution. And here we show the proxies of weathering proxies, and including the CIA and the potassium to allium and the keranite elite ratio and smectite to elite chloride, and also the terrigenous flux and the CO size to the clay size fractions and the ratio. And all these proxies like to show the very similar trend, and also shows that the stronger East Asian summer monsoon than before 40 million years, with maximum at 23 million years to 20, and also the middle Miocene around 17 to the 15 million years, and then general decrease since around 14 million years. And all these proxies is generally consistent with the previous monsoon proxies, including the sediment rate from the offshore the Pearl River, and shows the South China evolution, and also the hematite to goethite ratio at Old Beside 1148, and also the pollen assemblage in Sediment Basin, Lurth Plateau, and so the stronger East Asian summer monsoon during the middle Miocene and then decreased since the late Miocene. So one point is interesting point is that if we compare the global deep sea oxygen isotope, we'll see that the monsoon evolution, long-term evolution of Asian summer monsoon is in pacing with the global deep sea isotopes. And during from the Oligocene to early Miocene, during this warm period, we will have the stronger, the warmer the East Asian summer monsoon, and then after the late Miocene and the global cooling, and the monsoon proxy is likely decreased. So it seems that monsoon evolution is response to global climate change. And in fact, our previous studied from the northern South China Sea Olympic site 1146, but it's a shorter time, since around 20 million years, also reveal the similar trend and for East Asian summer monsoon. That is reflect by the rubidium to strontium ratio and also CAA, and shows the maximum the East Asian summer monsoon during the early Miocene to middle Miocene, and then decreased since the late Miocene. While in contrast, the East Asian winter monsoon were indicated by the yawning flocks in the South China Sea and also the North Pacific, shows a very different pattern as the East Asian summer monsoon. So this is very interesting. We suggest that global cooling may have largely reduced the amount of water vapor in the atmosphere. And because water vapor is the most important the gas in the atmosphere, and is dependent on temperature. And also the increased mean radial SST gradient will and thus weaken the Asian summer monsoon intensity. In fact, there is also some other studies shows the similar trend. For example, Professor Lu Huayu group, and also shows using the pollen records from the Weihe Basin in North China, and shows the decrease of East Asian summer monsoon since around 11 million years, and like in pace with the global cooling, and so here is a contradict. And so how about the influence of a Tibetan plateau? Because the GSM modeling shows that support the coupling between the monsoon intensity and phased Tibetan plateau growth. It means that a higher and larger plateau will enhance both summer monsoon and winter monsoon. However, we don't see this. So there should be another factors, maybe the global climate, global temperature, rather than uplift of Tibetan plateau that controls the East Asian summer monsoon evolution since at least 27 million years. So one possible is that the major body of Tibetan plateau just already there, already obtained a critical elevation just before at that time. So after the 27 million years, the long-term evolution of Asian monsoon is mainly controlled by the global climate change. So the second one is on the orbital timescale, glacial timescale, monsoon and weathering. On this timescale, as we know, this is the monsoon evolution is strongly regulated by the orbital parameters related to insolation, and also the internal feedback between the Earth system. And there are many studies about these timescale studies about the Asian summer monsoon. Here, I'm not going to review all this and just select some of the typical studies, including the Earth plateau studies and the Japan, offshore Japan, the Regularian records, and also the famous Chinese spaniderm and the hydrogen isotopes from the Aquila trough, and also the northern South China Sea. And here shows this proxy records the spectrum analysis of the proxy records. And in general, the evolution of Asian summer monsoon is tightly dominated by orbital, solar insolation, and glacial forcing. And we see all these proxies, excepting the Chinese spectrum, that show very clear that the 100,000 years, 41,000 years, and 23,000 years period, just the eccentricity and the obliquity and the precession cycle. So this is very clear. Here I'm not planning to just to talk about the dynamics of Asian summer monsoon on this time scale, and just to emphasize that on the 100 Ka period band and the East Asian summer monsoon intensity seems strengthened during the interglacials and weakened during glacials. So this is the general idea. You follow this idea, this monsoon evolution through the glacial, interglacial cycles, and also the wisdom theory. So we will expect that the cold and dry glacial should have a very weak continental weathering than the interglacials during warm and with warm and humid climate. So this is a reasonable assumption. And is also supported by the lead isotopes in North Atlantic. It shows the much lower chemical weathering intensity during glacial of the high latitude of the North America. The weathering, continental weathering, is much lower during glacial. So they just suggest that the silicate weathering during glacial has low contribution to decrease the CO2 level in glacials. Just because here is we shows that the ice core that shows the very interesting phenomenon about this, and we can see the CO2 level, CO2 concentration shows very clear glacial interglacial cycles that in pacing with the temperature change, and also CO2 level largely reduced during the glacial, about 1/3 reduced during the glacial. So one important question is, who drove this variation between the temperature and the CO2, and why the CO2 level reduced during the glacial? So this is a very famous mystery about the carbon missing during glacial. And there are many hypotheses to try to explain the carbon cycle on this time scale, including coral reef iron hypothesis, respiration, CO2, and Southern Ocean leak. And most of these hypotheses focus on deep ocean processes, including the biological, the physical, chemical processes. And very few that concentrate on the marginal sea. We know that during the glacial, the sea level will fall down to around 120 meters. And so this is not important for the deep sea, but it's very important for the marginal seas with wider shelf. Because during this time, during this glacial time, the sea level fall down and will expose large areas of marginal seas with wide and flat shelf. And this shelf will expose, and the exposed will become new land. This new land with loose sediment will be possible to be chemical weather and again. And so there is little consideration of carbon consumption of the glacial shelf weathering, and it's possible the transfer of carbon from the marginal sea to deep sea. And we know this is important because the following three reasons. First one is the CO2 consumption by low latitude chemical weathering accounts for 60% of global budget. So this means that the low latitude weathering in global scale is very important. And the second one is around 39% of the world's shelf area exposed during glacial northlands, and most of which just lies within the tropics, especially the West Pacific. So the West Pacific, the margin is very important. The third one is much lower amplitude of cooling in low latitude than high latitude. This means the low latitude, even in the glacial, will still very warmer, average 25 centigrade. That is very good for the chemical weathering. And also the pollen studies from the South China Sea that shows that as the sea level noseband during the glacial, the tropical slowstand, the rainforest and the mangroves covered the exposed sand shelf. So this indicates that the shelf during the glacial is still very warm and humid, and so it's possible for the chemical weathering. The key question is whether the chemical weathering of tropical shelf sediment intensified or weakened in glacial is in response to monsoon evolution or sea level change, and to what extent tropical shelf weathering contributed to glacial carbon cycle. And here we using the following strategy, materials and methods. The material strategies use the sedimentary cores from the river mouth and also from the deep sea to constrain the history of weathering continent and shelf and respectively during glacial, interglacial cycles. The sediment cores, including the river mouth and including the ZK20 from the Pearl River, JRDS from the offshore of the Taiwan, and the 337 PC in the Cheongdongnan Basin. That and also deep sea cores from the core TWS TW-1 S1-1 and from the northern, eastern, South China Sea and old side 1143 and 1144 in the slope to deep sea. And the methods we use clay minerals, structure meter isotopes, major and trace elements geochemistry. And most of this is focused on the clay fraction. And so here I first show the weathering record of Pearl River. This core ZK20 is in the mouth of the Pearl River and with water depths on around 6 meters. And this the data, clay minerals data, and shown here. And we using the leader isotopes and also the trace elements, rare earth elements ratio of the clay fraction to show how the prevalence evolved through time and in the Holocene. And it's very clear. The gray band is showing the leader isotopes of Bach, the sealed to clay fractions from the Professor Zhifei Liu. And here, in any case, we see that the long-term trend of the prevalence is relatively very stable and low, very large change. In contrast, the weathering proxies such as the Kernan to inlet ratio and the potassium to anion shows a very similar trend, and it just follow the trend of the Chinese cave record in South China, and with the proxies shows that the intensified during the early Holocene, and we marked values between the middle Holocene around 9 to 6,000 years, and then decreased between the 6 to 3 or 2,000 years, and then intensified again since around 2 to 3,000 years. However, because this period during the late Holocene, the monsoon is just is decreased or just not changed so much, and we interpret this as a response of human intensification, human impact. Anyway, the coupled evolution of chemical weathering in South China and East Asian summer monsoon intensity that between the early and middle Holocene suggests the very clear monsoon forcing on the weathering in South China. Okay, the second record is from the offshore of highland rivers. This around with the water depth 37 meters is around 20 kilometers from the far away from the Wanquan River, and it records the history of weathering of highland through the North Glacial. And similarly, we show the prevalence indicators, the needle isotope of the clay fraction. It generally shows a very stable trend of and is originate from the highland source, and the needle isotope shows that. In contrast, the weathering proxy, the Kernan-inlet ratio, it's a very similar trend as the East Asian summer monsoon, the cave record, and is generally the intensified chemical weathering from the glacial to the Holocene. And so this also supports the monsoon forcing on the weathering. And the third core is from the 337 PC in the Cheongdongnan Basin. This core is in deep sea in the slope with water depths more than 500 meters. However, the sediment prevalence constraints by structure meter isotope shows that it came from the Red River, and moreover, the leader isotopes also show the stable prevalence through time. So the weathering proxies, the Kernan-inlet CIA, and also the physical evolution proxy, the traditional flux, also shows a very similar trend of as the monsoon evolution and temperature, just from the stronger and to the reduced its trend, its strength, and through to the late Holocene. In contrast, during the late Holocene, this is in fact by the human activity. So anyway, we show the coupled evolution of chemical weathering and monsoon for the continent weathering. And in contrast, this is very different for the Taiwan. Taiwan, the sediment core JRD-S is from the Zhuoshui River mouth at 4 meters above sea level. And this sediment core, we also show the data. Anyway, we can see the linear isotopes shows the trend is very stable. The prevalence is consistent with the Taiwan rivers. And in contrast, the kernite elite also show a very stable, almost no change for the ratio of kernite elite ratio. That means that the chemical weathering from the glacial to Holocene, there's no any change and or remain very stable. This is very strange, but it can be explained in geological setting of Taiwan. Taiwan is very different with strong tectonic uplift rate and very strong activity of the seismic and typhoon and very steep relief for this case. So the sediment just have a very high physical erosion rate and faster erosion and transport from the continent to the deep sea. So then we will see that very low chemical weathering intensity and very low content of kernite. So we can summarize the two patterns of onshore weathering in East Asia since the glacial. And the pattern one is monsoon forcing and the East Asian continent, except in Taiwan, that increased chemical weathering from glacial to Holocene. In contrast, pattern two is tectonic forcing. Taiwan Island keep relatively stable chemical weathering from glacial to the Holocene. So after we reconstruct how the continental weathering evolved from the glacial to Holocene, we can try to see how the deep sea proxy records in the deep sea, how the change through time. And if they have the similar the variation signal of weathering through time, if this is just to confirm that it record all the similar signal of weathering onshore. In contrast, if there is not, maybe there is some, so that we can guess there is something happened during the transport from the shelf to the deep sea. So this is general idea. And we use the sediment core from the GWS-1 from the northeast South China Sea, just in the deep sea. The water depth is more than 1,000 meters in Taixilan Basin. And this core, we also use the linear isotopes and also the immobile trace elements of zircon to half-Lyram ratios for the clay fractions to show that the prevalence is very, very stable and is consistent with Taiwan came from the Taiwan rivers, but not the Pearl River. In contrast, the weathering proxies or the strontium isotopes and kernite elite ratios and potassium to anion ratios just shows a much higher, much stronger chemical weathering intensity during the glacial than the Holocene. So this indicates a more stronger weathering during glacials. This is in contrast with our expectation, with our reconstruction of the continental weathering. The two patterns, one pattern is stable, another pattern is just a stronger weathering during Holocene than the glacial. But this is very, very different, is reverse to these two patterns. So we guess this is just the subaerial weathering of the shelf sediments exposed during glacial. But during that time, the shelf was exposed because the sea level fall down. And the large areas of shelf exposed, and these sediments will be chemical weathering again. And during that time, there are also many rivers that developed on the shelf during glacial, and will evolve and transport the weathered sediments to the deep sea. So we see the proxy records in the deep sea. It's just a combined effect weathering from the onshore weathering, continental weathering, and shelf weathering. So this is very important and interesting. And some people may argue that this cycle of weathering praxis change is maybe also possible, is possible just the result from the prevalence change. For example, the Pearl River can maybe can provide some sediments during glacial because the sea level fall down, but because the Carinite is rich in Pearl River. However, this cannot explain here in this case because the distance is very long. We can see that even during the lowest level during the glacial, the start side is far away from the river, the shallow on the shelf during the glacial. And moreover, the leader isotope don't support this. We didn't see that the obvious change of prevalence from glacial to Holocene for this start side. So we further combine the weathering, the proxies, and also other climate parameters, and through time, through the last glacial, and this is temperature, the SST, Northern South China Sea, and also the Greenland isotopes. And this is the Monsoon proxies, including the Dengge Hulu Cave, the famous curves, and also the North China pollen, that's the pollen from the lake. They show the very similar trend for the precipitation. And this is the continental weathering proxy from the river mouth. It also shows similar trend from the lower to higher chemical weathering and in response to monsoon. And in contrast, the deep sea records from the northern South China Sea and the South China Sea, the three sides from the three start side, and this also show the much stronger chemical weathering during the glacial than the Holocene. So this is very, very different. And it's interesting that for the physical evolution rate as reflected by the terrigenous MAR, and we see that the most four to three times higher physical evolution during the glacial than the Holocene. It suggests a much stronger physical evolution of the shelf, of the exposed shelf during glacial. That there at that time the shelf it will enhance the erosion by the river developed on this shelf and transport more weather sediment to the deep sea. So just the onshore weathering is monsoon forcing, and sub-area weathering on the shelf is sea level change forcing. And not only since the last glacial, but also we can see this similar process occurred on the last four glacial interglacial cycles. And we can see it shows the sediment records from the Olympic site 1143 in the South China Sea with water depths more than 2,000 meters. And this site, we show many proxies, weathering proxies, clay, feldspar ratio, Ca, Carinite inlet, and potassium to anion. And all these proxies shows very clear and consistent variation with much stronger chemical weathering during the glacial than the interglacial. So this is very interesting. And also the prevalence, the proxies, Strong-Sherman Needham or Needham isotopes, just keep change very small and cannot explain the large range change of the weathering proxies. So we exclude the onshore weathering, submarine weathering, because there's some poor water evidence and suggest sub-aerial weathering on the shelf just to explain this phenomenon we saw on the sediment cores. And even since the last 1.1 million years, we using the ODP site 1144, and in the northern South China and ODP site 1143 in the South China Sea. That shows both southern South and northern South China weathering record shows a very similar trend of chemical weathering with much stronger weathering during glacial than the physical erosion, and shown by the terrigenous flux and then the interglacial. So this suggests this phenomenon is basin scale phenomenon, not just only the local phenomenon. And we also show the long-term evolution, high resolution record of the Carinite inlet ratio of the ODP site 11.3 since the last 5 million years. And if we look at the long-term trend, this long-term trend, the tectonic or the mini-year time scale is just, I said in the example 1, that's during the Pliocene, the warm period, and we have a very much higher chemical weathering and monsoon and intensity during that time. And then during the quaternary, with the cooling and temperature and we have slower and chemical weathering and lower rainfall. And here I just want to emphasize the glacial, interglacial cycles. On this time scale, you can see that almost even each period of glacial, interglacial cycles, we can see that the peaks of permanent elite intensity correspond to low sea level and lower cooler climate. This is very interesting. This is more clear during the quaternary. So, and moreover, the coherent oscillations of 100,000 years cyclicity for both proxies just became more evident since around MPT, the middle Pleistocene transition, around 100 years. And we have a more evident changes of sea level since the MPT. And so the much wider areas of shelf exposed, and then we see the much longer, much stronger chemical weathering intensity, and so this site. And not only South China Sea, but also the Western Philippines Sea, we have the similar findings. And here, this is MD 06-3052 by this study by Zhao Kai, and also they shows that the needle isotope, the provenance change is very stable, and in contrast, the physical evolution and also the chemical weathering and the intensity is rapidly uplifted and rapidly enhanced during the no sea level stand and around the marine isotope stage 6, 3, and 2. And during this time, you can see the sea level fall down to 120 or 100 and even more lower during that time. So this is confirmed. These are finding in South China Sea. So anyway, just we roughly estimate the CO2 consumption by tropical shelf weathering during the glacials. Just assume the difference between the geochemistry of the glacial interglacials and is a result of chemical weathering of shelf sediment during glacial, and also assume the around 40% of sediment that dissolved in shelf will be chemical weathered during the low sea level stand. And so we estimate the CO2 consumption by cyclical weathering of shelf sediments is around 0.16 TMol every year. This number is around the globe 1.4% of global silicate consumption. This number is very small. It seems very small. But if we assume the similar processes that occurred in the global tropical shelf, the volume of the silicate weathering for this process is very large. It's around 12%. So your estimated flux of tropical shelf weathering during glacial low stands represent 12% of global bucket and accounts for 9% of the CO2 removed from the atmosphere during glacial, and represent an important role in the observed glacial interglacial variations of CO2. And okay, this is the summary. I think the time is used, and I don't want to repeat it. And okay, that's all. Thank you for your listening. And this is a picture of the shipboard scientist of LDP 346, and here is review, me, and this is Professor Zheng Hongbo. Thank you.
Thank you very much, Shiming, for this sweeping review of sedimentological proxies for the monsoon around Asia. Now, if you have questions, please send them by chat or unmute yourself and ask Shiming. until questions from listeners come, I have a question for you, Shiming.
Okay.
In this last slide, you showed the variability in clay minerals over the last 5 million years, I guess, since Pliocene.
This
and
one.
there were very large variability in the kaolinite illite
Yes.
proxy in Pliocene. What do you think is happening there at the orbital timescales?
Yeah. Yeah, there is some change for the kaolinite illite ratio during the Pliocene. Yeah, you mean the amplitude of the variation?
The amplitude. Yeah, the amplitude is as big as in the latest Pleistocene. Just the frequency is different, but the amplitude is really high.
Yeah, the amplitude is much higher during the, I think, during the Quaternary, not the Pliocene.
See, from 5 million to 4.5.
5 to 2.5 here, this period?
To 4.5.
Yeah, you mean the variability, the frequency.
The amplitude of the variability in the kaolinite illite. It's really high. I'm struggling to understand what's happening. It's probably a contribution between terrigenous and subaerial weathering on the shelf at the high frequency sea level change.
I'm not sure, but the ratio for this period, for this the early to early Pliocene, this period, during this period, the high content of kaolinite illite ratios is the result of because during that time this is much warmer, and you know that the Pliocene warm period, and we have stronger weathering and stronger monsoon during that period.
So that's not driven by sea level changes in that part.
No, not related to sea level change during the period.
That's very interesting.
Yeah, and also you can see that the more clear cycles of 100,000 year cycles just occurred during the late Quaternary.
Yeah,
right?
Yeah, and that switches towards sea level changes.
Yeah.
Very interesting, and a cautionary example on how these proxies are used.
Yeah.
Thank you, Shiming. Questions, please?
Hello, that is Stefan Steinke. Hello.
Hi, Stefan.
Hello, Shiming.
Yeah.
Wow, I'm overwhelmed by all your proxy records. Very, very nice. But I have a question about the long-term evolution of the East Asian summer monsoon. Because when looking on your record, and if I'm going to compare it to the Farnsworth modeling studies, it looks completely different. Because that Farnsworth et al. Talking about a super monsoon, for example, and if you compare their modeled precipitation records with your geochemical proxy record, it looks different. Do you have any idea for this mismatch, or maybe I missed here something?
So do you have special just proxies for this? I'm not sure which proxy you indicate. Which proxy?
No, I'm talking about the Alex Farnsworth study in Science Advances, because they modeled the past the East Asian monsoon evolution.
So this proxy, you mean here is from the. Can you see me the mouse?
Yeah,
here.
I can see.
Yeah, I understand your question. Yes, Yes, I also noticed this, and yes, he just
but this is a different record, right? That is not.
Yeah, it's very different. Yes, very different. He showed that much stronger Asian monsoon since the late Marathon. You can see that it's strengthened since that. But I'm not sure.
Yeah, it's that's right. That's right. Yeah.
Yes. This record is just cited from the study of first worth. I'm not sure the name is correct, but yes, I'm not sure the. I'm not so sure about this proxy, and to my knowledge, and most proxies more just indicate the monsoon, the East Asian monsoon, at least East Asian monsoon, the precipitation that is decreased rather than intensified since that time. And here also you can see that the pollen record from the Glacial Basin in North China also just decreased since that time. And you also had a study from the Pearl River of the South China Sea. That's the old side 1146, right, Steven? Just using the SSS, the magnesium to calcium ratio, and also shows the decreased the runoff from the Pearl River since the late Marathon.
Yeah, that's right.
7 or 8 million years, if I remember that is correct. So
yeah, that's right. But maybe the interpretation of the data ADNO seawater record is not anymore that straightforward as it was a couple of years ago. Maybe that is also became more complicated.
Yes,
to explain that only with rainfall or river discharge.
Yeah, that's true. Yeah.
Mm. Okay, Shiming. Thanks.
Yeah. Thank you. Yeah.
Any more questions, please? There are no more questions left. Let's thank Shiming for a very comprehensive talk. And we'll see you next week at the series with the talk will be announced by Peter in the next couple of days. Thank you very much, everybody, for participating. Thank you, Shiming, once again.
Thank you, Liviu. Thank you, everybody.
Bye-bye.
Bye-bye.